Welcome back to the Taurus Report, the bull in the china shop of cosmology. Before we proceed to explain in depth how CGC, cyclic gravity and cosmology, can explain everything we're seeing in the Webb telescope, I will go through the entire thing step by step. I have to poke a little bit of fun at the objections that I tend to get. Oftentimes from people who haven't even read the paper, and they're objecting without even reading what I have to say on the subject. So, what about the power spectrum of the CMB, the cosmic microwave background radiation? How can your modified gravity theory explain that? What about all of the planets and moons in the solar system? Your theory has to be able to predict the movements of the planets right here in the solar system. What about the bullet cluster? That is a smoking gun proving the existence of dark matter. And what about elemental abundances, like the elemental abundance of deuterium in the universe? How can your theory explain that? And what about the precession of Mercury and the bending of light that general relativity explains so well? How about cosmological expansion? What about galactic rotation rates? How about time dilation? How about increase of momentum at relativistic velocities? Your theory needs to explain all those things. Well, it does. CGC does explain all those things, and we can throw in a few more, like planetary formation and explaining the gravity waves that we're detecting with the LIGO apparatus. So I would like to ask that before anyone launches criticism of the theory, that they actually read it, because they'll see that it does indeed deal with each of these issues and explains them all in a way that, in my opinion, is better than how they are explained in general relativity. So I would like to proceed now, going through the paper step by step, to explain each part of it, so that the viewer can have demonstrated for them that CGC does in fact explain all these things. So let us begin. If you would like to follow along, you can start by opening up a browser and just typing in Taurus Report, all as one word, .com. And that will bring you to our website. And there are a few different things you can do here. You can see us on Spotify or YouTube or Facebook. But here is a link to the paper itself, so that you can see the paper. So we can click on that link, and then you'll get some version of the paper, an online version. And if you wish, you can download it as a PDF. So I am just going to do that just to demonstrate it. And then in general, I like to have my window, the view, zoom, fit with. And so that's generally how I like to look at it. Now, going through it, some of this stuff we've talked about before. I mentioned Oumuamua in the introduction, and explained how this theory can explain the anomalous acceleration of Oumuamua. And so I'd like to go now into the central assumption of cyclic gravity and cosmology, CGC, to explain where, according to this theory, gravity comes from. And we will start with something people have taken a look at before, which is explaining gravity as a sort of van der Waals force. And I start there, though I'm not going to finish there. The van der Waals force depends on slight temporary charge separations that exist And I'd like to kind of show a picture of that to show you what I mean. So here at the Britannica, here we have a picture of, if you imagine an atom, but in general we think more in terms of molecules, but let's go ahead with an atom to kind of see what I mean. So if we look at this atom here, the little blue dots around the outside sort of represent the amount of time an electron spends in that position. So the electrons of orbiting the atom. And if it spends a little more time over on this left side over here, and the nucleus of the atom is charged positive, and if the electron spends a little more time over on this left side, then there's a slight charge separation, and this side of the atom or molecule would be slightly negative, whereas the other side would be slightly positive. Now, if you bring another atom or molecule near it, then you might see this sort of separation. Both of them have a more negative on the left and a little more positive on the right, and they have an attraction to each other because of that fact. It's important to grasp what this allows when you have charge separation like this. What this allows is, say, a molecule. Let's say you have a molecule that's very large, okay, where I'm going to just depict it sort of as a string of atoms here. Okay, and let's suppose this atom is like a little more negative on this side, a little positive on this side, a little negative on this side, a little positive on this side. And so I'm talking about a molecule with a string of atoms where you have a slight charge variation. Now, when I say positive on one side and negative on the other side, I mean very slight, very slight. Now, if you have another molecule nearby with charge variation, and let's suppose this molecule nearby has this sort of orientation. Now you can see that even though both molecules might be charge neutral, they would still have an attraction to each other based on an orientation of their slight charge separations. There would be a force of attraction between these two molecules. Does that mean that I'm saying that gravity is called by van der Waals forces? No, that's not what I'm saying. But I'm going kind of in a direction that starts from there. It turns out that van der Waals forces, they are too weak to account for gravity, and several people have thought about that and investigated it, and I quote some of them in my paper. I make note of that, and I believe that this paper by Cole proves that it's impossible for van der Waals forces to account for gravity. Now, the reason that I start there, however, is because I began thinking, is there some form of the electromagnetic force where we can have attraction between charge-neutral objects? Now, in decades past, there has been a kind of a broad general movement called electric gravity, which is very eclectic with lots of, it's hard to characterize it. But one of the ideas central to it is that the gravitational force might be explained by the electromagnetic force. And so the simplest version of it would say something like, if the sun was ever so slightly charged positive and the earth was ever so slightly charged negative, for example, then there would be an attractive force between the two. And maybe that might explain the gravitational force. Now, the problem with that is if we had a charge difference like that, that would be super easy for us to detect, and we don't see any charge difference like that. For all intents and purposes, large bodies like the Earth and Sun are charge neutral. And so it can't be as simple as that. It cannot be as simple as this is charged positive, this is charged negative, therefore they attract. If there is some sort of electromagnetic attraction, it has to be done in such a way that the two macro objects are charge neutral. So I started with van der Waals forces because the van der Waals force does allow for a pattern of positive and negatives. And if the pattern kind of matches up like a lock and key, then you could have two charge neutral objects attract each other. And so we could explain gravity with the electromagnetic force. However, as I just mentioned, again, it's not that simple because the van der Waals force is far too weak to explain this. So is there another version of the electromagnetic force, some theory involving the electromagnetic force, that can allow the macro objects to be charge neutral and yet explain this attraction using electromagnetism? I believe there is, and I am now going to explain the central assumption of CGC and how it can account for the gravitational force. First, let us lay some of the groundwork here. I'd like you to consider the force of attraction between two parallel wires. If you have an electric current, let's say I have two wires headed in the same direction. We'll pretend these are wires, and there's electric current where the current in both wires is flowing in the same direction. If the current's flowing in the same direction, these two wires will experience a force of attraction. So another way of saying this is if you have two charges traveling, oriented in the space, such that they are traveling in the same direction, they are going to experience an attractive force between them. And we can model that with this equation here. Here's a diagram, okay, where we have two wires, electric current headed in the same direction, and you can see they experience a force of attraction between them. And then this is the equation giving the magnetic field. And then this is the equation giving the force between them, where L is the length of the wires. This is a constant. I sub 1 is the current in the first wire. I sub 2 is the current in the second wire. And then D is the distance between the wires. So they will experience an attractive force. Since most of the mass of an atom is in the nucleus, we next need to consider the charges within a nucleus. Let's suppose I have some nucleus of an atom, and it is filled with neutrons and protons. There's a few things I'd like you to keep in mind about the nucleus. First, in spite of their name, neutrons contain charges in them, and they balance out to an overall charge of 0. But protons also contain charges in them, and they balance to an overall charge of positive 1. But my point is that because both neutrons and also protons contain charges within them, and here I'm talking about quarks. Quarks have charges of quarks have fractional charges. And so the only point that I'd like to make is that these fractional charges, like each proton or neutron is made up of some number of quarks, and each of those quarks have charges. And so a few things to note is that we have all these charges within the nucleus, and notice that they are constrained in how much they can move, like whatever the boundary, whatever we might consider to be the boundary of the nucleus. The motion of these charges is constrained, and that is very important. Why is it very important that all the quarks within the nucleus have their motion constrained? These quarks, protons, neutrons, and everything in the nucleus are vibrating and moving back and forth and changing position constantly at tremendous speeds and velocities. And whenever you have a charge moving, that is the definition of a current. Okay, so we have charges moving around the nucleus constantly, and so we have some kind of back and forth motion. And I say back and forth because the motion of the charges in the nucleus is very much constrained. And so we can roughly think of all these charges moving back and forth. It's not strictly speaking, limited to a simple linear back and forth motion, but there's going to be a lot of motion constrained by that nucleus. And so what we can, to oversimplify things, we can think of this motion as if we consider the motion of a single charge, whatever it is in the nucleus, we can think of it as a current where that charge is moving in one direction and then coming back and then going back. And so rather than a simple current, we might think of it as an alternating current. And so if we think of it as an alternating current, we're going to look at a sort of a simplified presentation of this situation by having two wires close to each other, but instead of a simple current in a single direction, both of these wires are going to have an alternating current. They are going to be moving back and forth. You're going to imagine a charge moving back and forth in each of these wires. Now, if you have two wires with an alternating current, an interesting thing happens. When the wires are in phase, that means if the charge is traveling together, when they are in phase, these two wires are going to experience an attraction. When they are antiphase, like let's say they are moving back and forth such that their waveform is opposite of each other, then they would actually experience a repulsive force. Okay, so in other words, if this charge is moving in this direction at the same time that the other charge is moving in the opposite direction, they are going to experience a repulsive force. And so the situation becomes, if you have two wires with an alternating current, the situation becomes much more complicated than if we're talking about two wires where it's a current in the same direction, a simple direct current permanently in a single direction. And so let's consider what this means for some macro object. Every macro object is made up of trillions and trillions and trillions of atoms. And if we think of each nucleus as a cauldron of boiling charge fluctuations, which can be, in an oversimplified way, be depicted as a alternating current, a very short alternating current. And by short, I mean the diameter of the nucleus. So you have this alternating current back and forth. And if each macro object is made up of trillions and trillions of these atoms with these short alternating currents, then we can, in an oversimplified way, we can sort of depict that with a diagram, which is done in the paper here, like this. So here we see, this is sort of a schematic where you have trillions of different charge fluctuations going on back and forth. And notice that the macro object stays charge neutral. Okay, so if it stays charge neutral, and this provides a possibility of an attraction between two macro objects if some of these fluctuations are roughly aligned with each other. So for simplistic purposes, I do a diagram here where I'm doing a schematic, say, of the sun and the earth, let's say. And let's say we have, I've highlighted in red here, two charge fluctuations, one on the sun, one on the earth, that are vibrating in such a way that they are in phase with each other, and they're roughly spatially aligned. Meaning, what I mean by that is they are parallel to each other. So if they are parallel to each other, and if they are in phase with each other, they would cause a very slight attractive force. And so if we take a look at that, that force of attraction, here's a simplified equation here. Okay, the force is going to be proportional to the current, let's say the current on the sun. And if it is going back and forth according to this trigonometric function, cosine function, and then we have the same thing on the earth here, where the current multiplied by this cosine function, basically this describes an alternating current. So here is the alternating current on the earth. Here is the alternating current on the sun. And if they are roughly in phase with each other and roughly aligned spatially, meaning parallel, then the force of attraction between them is going to be proportional to this. Now notice, if they're anti-phase, that force would actually be negative. Now, the electromagnetic force, whether you're talking about the electrostatic force between charges, or you're talking about the magnetic force, is many trillions of times stronger than the gravitational force. And because it is trillions of times stronger than the gravitational force, and when I say gravitational force, I'm talking about according to standard theory. Since the electromagnetic force is trillions of times stronger, you would only need a microscopic quantity of these fluctuations to be roughly aligned and roughly in phase in order to fully account for the gravitational force. Now, most of them are going to be kind of randomized, like let's say 99.9999% of them will be randomized with each other, and so the effect would be just random noise. But you'd only need some tiny proportion, like 1 in trillions, just one part in trillions, to be roughly aligned and roughly in phase to fully account for the gravitational force. So this suggests a new equation for the force of gravity, which I am going to go into next. So let us begin with, let's pretend we're talking about 4 different fluctuations on the sun. So I am looking at just this on the left here. For now, we're going to ignore everything on the right. So let's just look at what's on the left here. And here we have 4 different fluctuations. Maybe there are 4 different atoms on the sun, where there's some charge fluctuation within the nuclei of atoms, Or if portions of the sun are plasma, it could be fluctuations within the plasma. But be that as it may, whatever the source of the fluctuations are, just each of them kind of vibrates back and forth according to its own rhythm. So here, for instance, looking at this first one, the charge is traveling in this direction for a bit, then it reverses and travels the other direction, then it reverses and travels the other direction. So you can think of the charge as just moving back and forth. And so we have 4 of them, 4 moving charges. Now, if we combine them all here, you get this random jumble that doesn't really produce any force at all because it's just kind of randomized. Now, let us consider if we have 4 fluctuations like this on the Earth, and I'm not diagramming them, but they are in this chart here, where there are 4 fluctuations on the Earth that are not in phase and they're not really anti-phase. I gave them to start with just a random sort of fluctuation, not related to the ones on the sun at all. And each of the ones on the Earth I paired with its partner on the sun. And if they're kind of fluctuating randomly in regards to each other, then you'd add each of them up and you'd get this sort of random force. This yellow drawing right here, this yellow figure, shows the force of attraction or repulsion. If it's below the horizontal line, that means it's repulsive, okay, over time. So sometimes it's attractive if you sum them all up, sometimes it's repulsive. And so over time, you get this sort of random force going on. And there is no net force because it's just sort of random. However, what happens if some of them come slightly in phase? And so here is the equation where we have the force of a Sun-Earth pair all added up. So 4 of our pairs added up, and this would be the net force. Now, what happens if the phase changes somewhat? Notice what happens. Here, I assume that over time, 2 macro bodies in orbit around each other, like the Sun and the Earth, over time they become what I call acclimated, where some small, tiny portion of their charge fluctuations become into phase with each other. And as I said, it would be like 1 in trillions of the fluctuations occurring. All you would need is 1 part in trillions to come into acclimation with each other, where they are vibrating in phase and roughly spatially aligned or parallel. And then you would get this adjustment. So here I have them slightly like in phase and slightly aligned with each other. And then we look at the force here, and here we have a more or less constant positive force. And so this is a depiction of the gravitational force. And yes, there's some variation, but you're getting kind of a constant positive. And again, I said above this horizontal line means an attractive force between the Sun and the Earth. And so to put all this in the form of an equation, it would look something like this. Okay, this sum symbol, this sort of big E is like the Greek S. It's a sum symbol, and basically it's saying add up all those pairs, from I to N, however many pairs you got. Let's say you have 1,000,000 pairs. You'd add them all up, and if you add them all up, that is going to be proportional to your force. So let's explain this equation a little bit. I just want to explain each of the variables. This mu sub O is the vacuum permeability. That's a constant used in a lot of electromagnetic calculations. R is the distance between objects. And this K is an arbitrary constant that is meant to show that under this depiction of gravity, at micro scales, the gravitational force disappears and it becomes identical with the electromagnetic force. And so under standard gravitational theory, as the distance between the objects gets small, the gravitational force gets stronger and stronger and stronger, basically under standard equations going to infinity when the distance is zero. That is not, in fact, what we see, and there is no account of gravity at small scales like atomic scales and less. And so inserting this constant means that you can arbitrarily put a number there that is appropriate, so that at very small scales, the gravitational force would disappear. Then the omega and phi would be angular frequency and phase shift. And as I said, the index of the sum from I to however many partners you're talking about, that is what this refers to. Now, over time, as two macro objects become acclimated to each other, then they become in phase with each other, then the gravitational force becomes like this. And I say squared because the motions of the two charge fluctuations we're talking about becomes the same. And so this top equation 7 becomes this equation number 8. Now, what this acclimation means. So what do I mean by acclimation? What I mean is that two macro objects that are near, and I'm using the word near sort of in an arbitrary way, if they're near each other for a long time, like let's say the Earth has been orbiting the Sun for billions of years, they become acclimated to each other, meaning that some portion of their trillions of charge fluctuations become sort of synchronized and acclimated to each other so that the gravitational force stays very constant. Now, this is going to mean that there will be a very strong bias towards circular orbits. And it means that in a solar system that is first forming, you're going to have circular zones where gravity is stronger and matter will tend to congregate in those zones. And then you may have other zones where gravity is very weak or else even repulsive. In my paper, I just depict this, and we'll get to this more in later episodes. But in my paper, I show this star system, HL Tauri, where you can see very clearly what I'm claiming. You get this sort of ring system, and I'm saying the dark areas in the formation of that solar system are areas where gravity is either much, much weaker than normal or else even repulsive initially when a solar system is being formed. Now, going forward here, after this section, so that is what I mean by acclimation. That is what I mean by acclimation. Now, one result of all that is if you get some object that travels at high radial velocity, and by that we mean something that is not in orbit around the central mass, but instead travels radially, like directly at it at high speed, or else if the orbit is very wildly elliptical, so that they're kind of traveling directly toward the object before they whip around it. Any object traveling at a high rate of speed radially, the acclimation is going to break down, and we're going to start seeing gravitational anomalies, and we will talk more about that in our next episode. So I'd like to thank all of you for joining me once again here at the Taurus Report, and we will see you next week. Bye-bye for now.